Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be completing Chapter 17 on classification. In this video, we'll be looking at this example from a business school for admissions data, where we're going to admit based on unequal prior probabilities using discriminant analysis. And then I will show you the difference between linear discriminant analysis and quadratic discriminant analysis, where the quadratic simply drops the assumption that the covariance matrices between the groups are the same. So the admissions officer of a business school has used an index of undergraduate GPA and management aptitude test scores, the GMAT, to help decide which applicants should be admitted to graduate school. And the data below are going to give the GPA and GMAT scores for recent applicants who are either classified as admit, so these are people previously who have been admitted, people who are borderline, or not admit. And the reason in graduate school to have this borderline category is perhaps your program can admit so many students each year, and there's competition between students. Some students have multiple offers, get chosen, and choose a particular school. And so perhaps you admit everyone who is in the A category. Some of those people may not actually come to your school. And so in that case, you continue to fill the slots from your borderline group. And so right now, we're going to use an equal number in our training set from both the A, B, and N categories of admit, borderline, and not admit categories. And we'll take a look at the data here. So I'm going to read it in and do a GG pairs of the business data, and I'm going to color it by their admission status. Oops. And here is that data. So we can see that we have roughly equal frequencies for the three categories. Admissions are red, borderline is green, and blue is the not admit categories. And you can see some distinctions for the GPA scores as well as for the GMAT, though for GMAT, basically the admit group is a little bit ahead of the other two. The scatter plot matrix here I've made a bit larger on the plot on the right, and you can see the admit category has both high GPAs and high GMATs generally. The borderline groups have slightly lower for each, and the not admit looks like the distinction between those two groups is based on the GPA rather than on the GMAT score. So the officer wishes to use these data to develop a more quantitative approach to classify prospective students. Right now, the way the officer is using data is basically they'll look through an application and then make decisions based for each individual separately. And wouldn't it be nice to be able to just put a pair of numbers into a classification algorithm and have it give you its best guess, and then you can spend a little more time on students who seem promising from that first filtering from the classification algorithm. Historically, about 20% of the students have been admitted, 10% are on the borderline, and 70% are not admitted. And the officer would like to keep these percentages roughly the same in the future. So this is a natural place to use discriminant analysis, and we will pay a little more attention in this example to the underlying assumptions of normality and equal covariance matrices. In fact, let's go back up to these plots and take a look at whether normality seems appropriate. When we look at the marginal histograms, each of these to me looks not too bad. Looks like the reds here, there's a few extra in the high, or the GMAT scores, a little bit extra on the high, but these tend to be roughly symmetric. Possibly different variances across these GMAT scores. Similarly for the GPA scores, the GPAs maybe, I don't know, these are actually fairly similar. They're all unimodal, roughly symmetric. Not too bad, actually. There's a few maybe outliers in the blue group for the GPA scores. At least univariately, this doesn't look too bad. Bivariately, so we're looking basically for ellipses, and I'm looking at the A group initially, and there's a few points over here in the B group range. The points almost look a little more clumpy in the middle than on the outskirts, but that's sort of what you expect for a normal bivariate normal distribution. The B group actually looks really good, except for this one up here. So, you know, this person probably ended up being borderline because they had really good scores, but maybe there's something else in their application which is questionable. So, but this looks roughly normal. And these N scores don't look too bad, possibly a couple of outliers. Maybe we'll have some tests for those shortly. All right, so all of this basically summarized what we just discussed. I'd analyze the data on this scale. There are a couple outliers, but we'll look at the variance covariance matrices a little bit later. And there is a fair amount of overlap between the borderline and the other groups, and that's not surprising. That's sort of what borderline perhaps suggests. There definitely seems to be a pretty clear distinction between those who are admitted in red and not admitted in blue. In fact, I could draw almost a vertical line down here and separate those by GPA. And then the borderline group is there in the middle. All right, so let's keep going with the analysis. I'm going to start off by calculating the covariance matrices, because the assumption here of constant or the same covariance matrices across groups possibly doesn't seem reasonable. So let me get all three of those on the screen. They're the covariance matrices, and in terms of variance, they're not too dissimilar, at least for GPA. For the GMAT scores, it looks like the borderline group has slightly less variability. And the off diagonals, we have positive here, negative here, and a bit more positive here. So it seems that there's maybe a little bit difference in the orientation, basically, of the correlation. And for some reason, when I last compiled this correlation matrix didn't generate the correlation matrices. So apparently I need to fix my code. But the main feature in those covariance matrices are probably that we've got positive correlations for the admit and non-admit, but negative correlation for the borderline group. And that difference in correlation is going to be indicative of possibly non-equal covariance matrices. So let's use our partition matrix from the KLAR package and classify the three admit groups using the GMAT and the GPA variables. And I didn't specify, but I think the default here, these are curved. I think this might be the quadratic discriminant function. Not sure. But one thing that we see in this partition matrix is we have about a 15 or about 16% error rate. But you can see this classification rule has different lines depending on which pairs of groups are being distinguished. So we have a cyan area, which are for all the accept groups, and we have just a few accepts who are misclassified as borderline in the white group, so these red A's. We have some red B's, which are borderlines who are classified as accepts. And then the cyans, we've got, sorry, this is the magenta group for the not admit. We have a couple misclassifications there, but generally not too bad. So imagine you have a new applicant, and the new applicant value appears here, where my cursor is. You'd classify that as borderline, because it's in the white area. So immediately, just with these two values, GPA and GMAT, you can have a guess at whether you're going to accept them or not. If we perform the LDA on this data, we get two linear discriminant functions. One has a fairly strong negative GPA loading, and the other one has a negative GMAT loading. So those two together account for about 95% of the predictive ability, and because they're both the same sign, as LD1 increases, both of these decrease. So if I take a look at this plot, if the direction that where LD1 goes is on this positive diagonal, positively sloped diagonal, as LD1 increases, it heads from the upper right down toward the lower left. They both become more negative. And that's generally the pattern that we see in what distinguishes those three classes. All right, if we plot the LDA, we see that, or the LD1, the first linear discriminant, we get group A, group B, and group C, and this is the direction that makes them the most different. You can see quite a bit of overlap between the borderline and the other two groups, though very little overlap between the accept and the not accept. So these two features, GMAT and GPA, don't help us to classify applicants perfectly, but it gets us a long ways toward making those admission decisions if we were an admissions officer. Let's perform cross-validation to see how well this is likely to perform in the future, and we're going to do the jackknife, which is a leave one out cross-validation. It's the n-fold cross-validation. Here's the set of columns that I've been creating with the classification error tables. And if we look at the summaries for this, we take a frequency table of what the true admission status was versus how we were classified. We classified most of the admit students as admit, but 6 of them as borderline. But we didn't confuse any admit with not admit, so that's pretty good. For the not admit group, basically the same thing. We classified some not admit at borderline, but not as admit. So for me, that's those two groups, the ones that are furthest, it's a nice result to see that they separate. The borderline group is in the middle, but look, we only get 3 misclassifications for admit and for not admit. We get most of those correct as well. So we're already doing, with 2 numbers and this classification algorithm, almost as, basically just as well as someone doing all this admission stuff by hand, and it hasn't taken us any more time than it would take to type those numbers into a spreadsheet. All right, so the overall total error rate here was about 17%, but there are errors that really make sense. It's really confusion with the borderline group. All right, so the last part here, the last 2 parts, are to include in our classification algorithm unequal prior probabilities, and then to relax the assumption of equal covariance matrices. So in the admissions example, historically 20% of the applicants were admitted, and 10% were borderline, and 70% were not admitted. So we want to build those percentages into our classification rule by specifying the prior distributions. And the way this works is we have our distance rule, our Mahalanobis distance, and this first part that's highlighted is the Mahalanobis distance that was defined before. Previously, we assumed that the prior probabilities were all equal, and so there is this penalty term, but because they were equal for all the groups, I didn't bother discussing it at that time because it affects all the groups equally. Now, membership into a group, meaning what's the distance between our current observation and the mean for group J, well, that distance now depends on what the prior probability is. And so if this prior probability is low, say it's close to 0, then log of a number that's close to 0 is very, very small. It's close to negative infinity. It goes negative quite strongly. We're going to multiply that by 2, and we're going to make that a negative sign. So this number that's sort of close to negative infinity, minus that becomes close to positive infinity, so that distance goes way up. So that becomes far away. Whereas if we have a high prior probability, say a prior probability close to 1, log of 1 is 0, and so we basically don't add any penalty at all for that distance. So this is a log penalty on the prior probability, which goes into the squared distance between the observation and the group for which you have this prior probability. And then that goes into calculating those posterior probabilities in just the same way. It's the ratio between the exponentiated squared distance divided by the sum of the distance to all of the groups. So that's pretty straightforward. This S is still the pooled covariance matrix, so we're still making the assumption right now that the covariance matrices are all equal. And so our main addition in this step is to specify different prior probabilities for our three groups. And in our example, we're going to have 0.2 for admitted, 0.1 for borderline, and 0.7 for not admitted as those prior probabilities. All right, so I'm going to add 6 new observations to the business data set, and here they are. So I've got an admit status which is missing, but then I have 6 GPAs and 6 GMAT scores that I'm going to add, that I'm going to use to predict. So with priors, the LDs are different, so the linear discriminant functions are different, so I'm going to need to recreate my LDA.business object using LDA, and here's my prior, 0.2, 0.1, 0.7, and it's important to know that this order is in the same order as the factor variable for admit. So because the admit labels went alphabetically, admit, borderline, not admit, that's the order 0.2, 0.1, 0.7 that we're using. Fortunately, when you look at the LDA business output, it actually tells you what those priors are so that you can match them up. So make sure that A, B, and N actually match up with their correct probabilities as they do here. So we've got the group means, we have the coefficients for the linear discriminant, and basically these two signs are both negative, so it's again that positively sloped line that basically the same as before, and this is going to account for 98% of the predictive ability. The second direction doesn't help that much. If we look at the, so we're not predicting the new observations yet, we're just getting a sense of how well our model is predicting with these new prior probabilities. So if I use the LDA and perform cross-validation using these prior probabilities, put that in here and create the classification table that I've been making. Oops, sorry for jumping around. And look at that table, and here I'm just looking at the errors. So I've excluded any observation where the error was blank. We have a sense of what the errors are. So the admits are sometimes confused with the borderline, but now some of the admits are confused with the no's. Borderlines tend to be more confused with the N's than the A's, and that's partly because the N's have a higher probability of being included or being classified as an N, 70%. And you can see for many of these, the posterior probabilities are not that definitive. So in this second case, the posterior for the not admit group was 0.5, but then we had a 0.4 and a 0.1 for the other two groups. There are some that are definitively incorrect. But boy, look at this one. This is almost equal probabilities for being in the borderline or the not admit group. So now if we look at our classification ability, we have A's are being somewhat misclassified, borderlines are being a little more misclassified, even the N's are misclassified, some of them as A's. So those prior probabilities have started to make a difference in how well we're classifying. All right. And that actually increased our error rate up to almost 25% or 23%. All right, so let's classify using the predict function the new data set, the new observations, and take a look at what classification that has done. So we didn't have an actual admit status for these. We've classified them as N's, A's, and B's, and it looks like we classified 2 in each group. And most of these classifications are fairly definitive in terms of their probabilities. This one here is basically pretty equal. Those last two borderline cases are pretty equal. And that's partly because the borderline prior probability is only 10%, 0.1. And so it's unlikely to be classified into the borderline group. You basically need strong evidence to be in the borderline group versus the others. And because the borderline group overlaps so much with the admit and the not admit groups, there's so much overlap, it's hard to get strong evidence of being in the borderline group. So this result for me is not surprising. All right, so the last detail is about using unequal covariance matrices. And it has, from what I think is sort of an unusual name, when we have equal covariance matrices, that's called the linear discriminant analysis. And when we don't assume equal covariance matrices, unequal covariances is called the quadratic discriminant rule. Okay, so that's just the name that's been given to it. And the addition is in our distance metric. So we're building everything into this distance metric. We've got the original Mahalanobis distance as the first term. We have possible differences in prior probabilities as the second term. And then finally there is a measure of the covariance matrix. This is actually the 2 vertical bars indicates that you're taking a determinant of that covariance matrix. It's a linear algebra term. And we're going to look at, and the determinant of the matrix is a single number. So we can take the logarithm of that single number. And so if a matrix is highly variable, meaning we have big variances in this covariance matrix, this is going to be a large number, and the log of that number will still be fairly large. And so big variances will greatly increase the distances. Whereas if you have really small variances, this log is going to be relatively small, and so you add a small penalty. So we end up adding bigger penalties for more variable populations. And that sort of makes sense, because if a population has a big spread of points, it's more likely to overlap with other groups, and there's just more uncertainty. Whereas if you have small variability, then the population's more precise, and so you're going to have smaller distances. So all that's working in the direction that we like. Also the last addition also is over here in the Mahalanobis distance. Instead of using the pooled covariance matrix, we're now using the group-specific covariance matrix, which allows the distances not to have to align all in the same direction. So where we had the example before here, where all these covariances were positive and in this positive direction, now you can imagine group 3 as having maybe a negative covariance and being shaped in the other direction, so that distance metrics are specific now to each group rather than being shared between groups. But we're going to calculate our posterior probabilities the same way once we've calculated our distances, and we can perform classification from that. So let's look at the difference between using a linear discriminant analysis versus a quadratic discriminant analysis for the business data set, and we'll just finish off by looking at a few plots. On the left, we have the partitions of the space for GPA and GMAT based on the linear discriminant analysis. There's an error rate of 15.7%, and which is not bad classification given that the borderline group has so much overlap with the other two. On the right is the quadratic discriminant analysis, and the main feature you're seeing right away is how curved these lines are. Those curves are based on those penalties for the differences in covariance and the differences in the prior probabilities. Same thing here, the curvature here is based on the differences in the prior probabilities partly. And our error rate went from 15.7 down to 14.6, basically 1%. Not a big difference. In fact, you can identify where it made a difference. This 1B in the middle was correctly classified where that B over here was misclassified, right on the border. And along this line, the cyan and white border, we actually got, over here on the left, we had A correctly classified and B misclassified. And then on the right, now we have A misclassified and B correctly classified. So that was a split. So the only real difference was this 1B, which was on the border of the borderline group and the not admit group. So in this case, it didn't make a great difference, but you will find data sets where these differences are much more extreme. Basically, the differences in the covariances between each group, and it can really help out in those cases. This last part is just doing cross-validation using the quadratic discriminant function, and we're basically getting very similar results as the linear discriminant analysis. And I think we get the same classification as we did before on the new 6-observation data set. And that is the end of a long classification chapter.